Welcome everybody. So we have now built, given a set of formulas, a model built out of terms. Okay, so we have this model built out of terms and an equivalence relation on the terms that tells you which terms should be equal, and we also know how to apply the functions on the terms and apply relations on the terms. So we have a full tau model, if tau is your vocabulary. Now the question is, what does this model satisfy, right? So we saw in the examples at the very beginning, let's see, for instance here, that on this vocabulary with identity, an operation, and a constant symbol, if we take the group axioms, we get something that is called a monoid. It's close to being a group. It satisfies associativity, it satisfies that the identity is the identity, but in this case we have no inverses. All the elements we had looked like identity, c squared, c cubed, c fourth, essentially look like the natural numbers. And actually if you do the operation on this one, you're gonna see that this looks like the natural numbers with addition. So it's not really a group because it has no inverse. So it's not that good. Then we saw another example where we added the inverse function as a function symbol. So now we can build terms that involve the inverse function. And now, well, in this example, this particular example, we had two letters, A and B. We could have had one. So now we can build anything that you can write with the two letters, the two constants A and B, A times B, I minus 1, B, and multiplying and using the minus 1 operation, the inverse operation. And we saw that what we get is everything that can be written as a word concatenating A's, B's, A inverses, and B inverses in a way that if you have two of these together, they cancel out. So we got a group. In this case, we got a group, and we are happy because we started with the group axioms and we ended up with a group. So one thing to notice, in the previous case, we also had the inverse axiom. The group axiom contains a sentence that says that for every x there exists a y such that x star y equals the identity. So that's part of the group axioms here. Except the reason we didn't get an inverse in our model is that we don't have a term that builds the inverse, right? We are building this term model, so all that we have here are terms, closed terms. So if you want an inverse, you have to have an inverse, you have to have some way of building it as a term. So this axiom just tells you that there exists something that is the inverse, but it doesn't give it to you as a term. And that's why the inverse is missing in this term model up here. And even though the axiom is there, while in this case, the inverse was there. Okay, so that's all to say that it's not that simple. The term model doesn't satisfy everything that we want. But let's start seeing what it satisfies. So one thing that's going to help to satisfy more things is to assume that our set of formulas is maximal consistent. Okay, so remember, maximal meant that for every sentence phi, either gamma proves C or gamma proves the negation of phi. So it must prove one of those two. So that's not true for the case of groups, for instance, right? So you can write a sentence that says the group is abelian, and the group axioms don't prove that the group is either abelian or not abelian. They don't prove either. So the axiom for group is not maximal. But if you assume it's maximal, we're going to have better properties. So the theorem says that if you're maximal and consistent, and phi is a quantifier-free sentence, so it's a sentence that uses no quantifier. So it's built out of atomic formulas using just, negation, and or implies, and the sentential connectives essentially, but not quantifiers. And it's a sentence, so it also has no free variables. Then this formula is satisfied in the term model if and only if is true in gamma. So let's see why that's the case. Well, we have to start with atomic formulas. For the atomic formulas, we pretty much know this is true, right? We know that if gamma proves that some term S is equal to another term T, then by definition, S is E-related to T, right? And then by definition of the term model, we get that in the term model M gamma, S equals T, right? Okay, so that's for that direction. What about the other direction? Well, the other direction is the same, because actually we know that by the definition of E was an if and only if definition, right? So that's exactly what defines E. And we also know that definition of the term model, two things are equal in the model if and only if they're equivalent. So these are all like if and only ifs. So this is very clear in that case. For the relations, we have the same, right? So we know by definition in the last video that if gamma proves that R holds of terms T1, Tk, we have it right here, right there, we get that the term corresponding to T1, term corresponding to Tk, so these are the equivalence classes of these terms, belong to the interpretation of R in the model. And that is exactly the same thing as saying that, by definition of what it means to model something, that M gamma satisfies R of T1, Tk. Right, so for atomic formulas, this is the case. This is true. If gamma is of the form psi and theta, then we can apply the induction, because we can assume we know the theorem is true for theta and psi, and use that for phi. So let's see what we get. Well, then gamma proves psi and theta if and only if gamma proves psi and gamma proves theta. Why is that? Well, this is because of the rule T. Rule T, remember, says that if gamma proves a bunch of things, alpha 1, alpha 2, alpha n, and all these guys tautologically imply beta, then gamma implies beta. Okay, so that's what it says. So if you can prove this already and they tautologically imply beta, then you get beta. And why is that useful? Well, because we know on the side that psi and theta tautologically imply psi, right? If you have psi and beta true, then psi is true. And also psi and theta tautologically imply theta, and also psi and theta together tautologically imply psi and theta. Right, so all of those are used right here to get that those two are equivalent. And now we can use the induction hypothesis, because psi and theta are smaller than phi, and we get that this is the same thing as having that M gamma satisfies psi and N gamma satisfies theta, right? That's an induction hypothesis. We know this is equivalent to that, and that is equivalent to this, because they are smaller. But now, again, now by the definition of what it means to model an AND, if you look at way back when we define what does it mean to model something, this is the same thing as modeling psi and theta. Okay, so far we have not used the fact that gamma is maximal. To prove an atomic, we didn't use anything about gamma, just that it was a set of sentences. So that means if something is built out of ANDs and atomic formulas, then it's preserved if it's true in gamma, if and only if it's true in M. Also, if you use OR, you're going to see that it's preserved. The interesting case comes when you do not. If phi is of the form not psi, then what do we get? Let's see. The gamma proves phi if and only if gamma does not prove psi. Why is this? And this follows from the fact that gamma is maximal and consistent, right? So maximal means that gamma must prove either phi or psi, one of the two. And consistent means that it cannot prove both, otherwise we get an inconsistency, right? So maximal and consistent means that we always prove either the formula or the negation, and that's it. Those are the possibilities. So if you prove one, if and only if you don't prove the other. Now here is also an if and only if up here. So by the induction hypothesis, psi is a smaller formula, we get this is the same thing as saying that, sorry, M is not true. In M, psi is not true, right? That's the same thing. And then that is equivalent to saying that in M, phi is true, right? Because phi is a negation of psi. So we get what we wanted, right? We get what we wanted in all cases. This if and only if that, this if and only if that. So in all cases, we satisfy these things. There is also the case for implies, ors, if and only if. We know those connectives can be built out of these ones. So we don't need to do those proofs because everything should work the same way because we have the tautologies. So you can try them out. I actually recommend you guys try them out. But it follows from these guys. So we get that at least for quantifier-free formulas that don't have quantifiers, if they are in gamma, then they are satisfied by the term model, so long as it's maximal. And maximality was used very importantly for the negation. You wouldn't get it otherwise. Cool. So, but what we want is to build a term model of everything, right? To prove completeness, to prove that if you're consistent and you're satisfiable, we want to build a model of everything. We don't have that yet, so that's gonna come up next week. See you guys later.